Hello everyone and welcome in this new recording, a new devlog session. This time again on additional WebGPU native symbols. We continue from the previous session where we just covered actually two symbols. And this time we're going to try to go a bit faster, and this means I'm going to give less details because I really need to get all this covered, and I want to keep working on what is currently the up-to-date status, which is this example implementation here. So let's start to start right now. Next thing we have implemented is a textured quad. Again, this was an example coming directly from the C package. Let's just try to run that in VB. WebGPU texture quad. Oh, come on. No. Oh, textured quad. Maybe. Yes. And yeah, I kind of remember that this one was broken now. It was not working anymore. It was supposed to display a simple quad, and for some reason, nope, it's not working anymore, and I need to investigate this, try to clarify, because right now I have no clear idea why it's not working anymore. Never mind, let's just move to the next one. Next one was trying to push this a bit further and trying to display a textured cube. Why was that different from what we were already doing in the previous examples? I'm not quite sure. We are loading PNG images. I guess I didn't have the support for PNG images at first, and I have introduced that in this implementation here. But this was going to go anyway directly into the texture loader subsystem that we already mentioned here. What else? Refactoring GLTF to support VBO and IBO usage. Yeah, I think at first maybe I was not really using this directly, but again, I have mentioned that in the base class that I'm using, which is a WGPU GLTF model. So when I load the GLTF model, at some point I get this object, and then I can retrieve VBO and IBO objects per vertex format, because when you have multiple meshes in a given GLTF file, those meshes may contain different kind of data. For instance, one of the mesh could contain the position, normal, and texture coordinate for the full mesh, so for all the vertices. So this is one vertex format from my perspective. So you provide position, normal, texture coordinate, and another mesh in the same file could provide the texture coordinate, the position also, and the color maybe. This would be a different texture, different vertex format, sorry. And the idea is whenever I have different vertex format like that, we have to use different pipelines to do the rendering. But if we have a single fixed vertex format, we can in fact collect all the vertices from all the meshes that are using this specific vertex format. We can combine them together in a big buffer, and then we can use a single pipeline to render all those meshes. Actually, it's a bit tricky because you have to take into account that, okay, you're going to render the first mesh using a sub part of your buffer, with a given pipeline. But when you use the rendering for the first mesh, you also have to apply a specific model transformation matrix, for instance, because it depends on where this mesh was in the hierarchy of nodes in the scene. And when you move to the next mesh, you have a different model again. So the final idea, I'm not quite sure it's fully implemented yet, but the final idea is that whenever I'm going to render those meshes, we have an additional buffer on top of that, or I don't know exactly how it's working anymore. This additional buffer will be responsible for providing the model matrix or something like that. But I think for now I'm not really considering that, and I'm just rendering a single mesh, most probably. To be clarified one day if we need to. For now, let's not lose too much time on that. Anyway, so let's try to run the textured cube. And this time, yes, we have this cube rendering properly. Let's just have a look maybe at the code itself to see what is really worth noticing in there. So as usual, everything is happening in the setup app function. You will see that the code is starting to get quite short now and clean. So we're just going to create a camera. Okay, we set up the perspective and look at position, but anyway, we are going to assign a target camera controller to this. Then we create a buffer with UData. UData is this containing those matrices. Okay, that's business as usual. This is what you need for the camera. Then you start creating those render nodes. So you create a render node with a specific vertex format. This vertex format must correspond to the model data that you want to load. And where am I loading that? Oh, I think it's here, in fact. When I do add drawable, this is actually going to load the GLTF file actually for the cube.gltf. So yeah, this render node mechanism is simplifying a bit everything, because you can just in fact define your binding group layout directly on the render node. Now you don't need access to a bind group builder. I think this was the name of it, because there is one inside the render node. And so you can define your binding group layout, and then you can add a bind group using this layout. 0 here means I'm using the layout number 0, which is this one. So that's defining uniform buffers. Then you have a definition of a sampler, then you have a fragment texture. And so when you build a group, you're providing the uniform buffer, a linear sampler in this case, and you're binding this texture, PNG texture. And then you request to add a drawable, which is again a subclass that I have added, encapsulating everything you need to actually draw something when you have the pipeline already set up and in place. So here is going to retrieve the model from the GLTF model, and the argument 0 here means you're going to use the bind group defined here, the first bind group which is defined here, and it's going to be assigned to this drawable. So that's it. Then you create a render pass and you add the bundle corresponding to this render node. Okay, and this is a result. Next. What do we need to mention here? I think I've covered that. Binding builder for render node construction. Okay. Plate buffer from struct. Okay, maybe I could not do that first. Okay, but now I can. The cube map added support for WGPU camera. Yes, at some point I was thinking that it was nice to have this basic camera object that I was recreating in a very simple, but I could also just as well try to encapsulate that into a dedicated WGPU camera. What is this? That's my sound. Okay. I think this one is actually providing also the buffer containing the camera data directly. So it's going to allow you to upload this buffer whenever the data is changed and encapsulate all of this. Cube map texture generation. Yes, that's another part that was extended on the texture loader system. Let's just try to have a look at that. Cube map. Here we go. So the first try I did was actually a simple cube map like that, but I was not really controlling yet the position of the camera in this example. So in fact, I'm still using camera that is rotating around the center of the world here, and the cube map itself is a cube centered on this point. It means that whenever I'm getting inside, you will see here we have some kind of distortion of the image because the camera is never really at the center itself, because it's always looking at the center. So there's always a small distance between the camera position and the actual center of the world. So that's not really an appropriate rendering for a cube map. But that was a first attempt. And if you, depending on where you're looking, you may not really notice, well, you see here that it's not really straight lines anymore, and here also, blah blah blah. But yeah, we'll get to this anyway, very soon. Do I need to cover the code for that? No, we need to go fast. Then what do we have? The skybox. Skybox was, yeah, the actual proper, what I mean actually first when I was mentioning cube map, because you can have a cube map for many different things, but if you want to have a skybox rendering, the camera must really be at the center. So this is what we did next with the skybox example. So we can just render this one. And starting with those examples here, the tricky part was more on the implementation of the shader. So basically this is the logical step. First we have to implement the basic element for the engine, but progressively the complexity is going to shift into the implementation of the shaders. So in this case, we have a proper skybox rendering. You won't notice any kind of weird transition or not straight line anymore. And so we may just open the skybox maybe. Again, the code itself is going to be pretty simple here. You're going to use a skybox shader. Prepare a render node from that, define a binding group where you provide the camera buffer size, a simpler and a fragment cube texture, and then you define a binding group. I mean, first you define the layout, then you define the binding group with the camera buffer, linear simpler, and this is your cube map, so your cube texture. And you just try to draw 3 vertices. This is a small trick, in fact, that I think it's quite known. You can actually render a full screen align quad with only 3 vertices. the trick is to try to draw a triangle which is bigger than your screen. So you start from one corner of your screen, for instance, but then instead of going to in clip coordinate, you would start at +1 in y direction. Then instead of going to -1, you would go to -3, and so +1 -3 in the y coordinate. And then on the x direction, instead of going to, you were on -1, instead of going to +1 on the x direction, you go also to +3. So +1 here, -3 here, and +3 in the x direction here. And this will in fact cover completely the area of -1 to +1 in x and +1 to -1 in y. So you're covering completely your clip space with only 3 vertices. This is what we're doing in fact in the skybox WGSL. So we received the vertex index, and I'm going to, yeah, this is a trick to get the position with the vertex index, and it's exactly doing the same thing as what we're doing here. So what we were doing here is what I said, so -1 -1 in fact, and then +3 -1 -1 +3. So yeah, then you build your invert model view, you unproject, blah blah blah, and this is what you use to sample your cube texture in fact from the center of the world, and this is where your camera is in fact. Yeah, I could, like, if I focus on that, I can build an understanding of it, but right now that would be pretty long to try to explain this. So this is 3D algebra, and yeah, if it's not really obvious at first, you need to focus on it and it will become clear, hopefully. Anyway, skybox, then the texture 3D. Okay, in this one I was trying to generate some Berlin noise, okay, and I will first try with fast noise 2, but was not really working with unscripted, because in fast noise 2 you're going to use a lot of sim acceleration and assembly code even sometimes, I think. So a bit tricky to compile that for unscripted. I could not do it, at least, so I just gave up at some point. But you also have the fast noise light, which is a simpler version, and it's actually providing different implementation out of the box, even GLSL or HLSL, not in WGSL unfortunately. But actually I didn't really need that, because the generation part wasn't on the CPU anyway, I think. Signed 3D texture, okay. Added time uniform. UBO provider, what was that? Good question. Bind multiple UBO provider with a single function call. Multiple UBO, oh okay, something like that. Yeah, I think I've defined. So add bind group, define bind group. You could define that, yeah, there's a first uniform buffer, then a second one here, then a 3D simpler, then a fragment 3D texture, and you can bind both of them at the same time again. So the camera and the frame context. So probably we're defining before that the camera UBO provider and the frame context UBO provider. Let's have a look at this one, texture 3D. So add UBO provider camera, that would be our camera itself, which is now a WGPU camera. This is encapsulating the row level camera, as I said, and it's providing the controller on top of it, providing the buffer that will be pushed on the GPU side. So yes, you just need to create a single instance of that, and everything else is encapsulated. Then we are creating another frame context from a frame context provider. Yes, not sure what this one is doing. It's a UBO provider, okay, and every time you do an update, you're going to get the current system time and also the frame number. Okay, that's all we have for now, I guess, and the delta time also. So the data that we can send is this time, delta time, and frame number. Okay, and I guess, yeah, this part was for the generation of the 3D Berlin texture done on the GPU. Then you create a 3D texture from this data that you have created just before. You create a render pass and you render the skybox first. So that's a dedicated render node because you will have a dedicated pipeline to do this rendering. Then you can add another render node, which is just another pipeline then to render this time a simple cube. So we have a dedicated shader textured cube 3D here. We're going to provide the two context that we have created before, and we're going to request a drawing of the cube model. And if we just have a look at this shader program, we'll see that we have a definition for the camera UBO and the frame UBO now, which contain exactly what we defined on the C++ side. And this will be provided as a first binding in the group number 0. That's it. Then you're just going to render the cube object, updating its position and providing the coordinate to the shader, the fragment shader part. And then on the fragment shader part, you use those coordinates, which are 3D coordinate in this case, because the third coordinates are you use 2D coordinate first from the vertex buffer data, but then you had a third dimension using the current time. And so you're going to get a different slice of your 3D texture depending on the time display on each face of the cube. And so you sample your 3D textures this way, and you just why do okay because yeah, my texture is actually one-dimensional. I mean, not one-dimensional, but it's not RGB color data that I'm providing, I guess, because what we have here, it's just generating a single noise value. Yes, so we have one float 32 value per pixel in this texture, per pixel. Okay, and let's just have a look at, oh, what did I do? What this is looking like. Textured cube. I think that's it, right? No. Oh, it's texture 3D. I don't remember what's the name of the. Yes, that's texture 3D. So yeah, we have the same skybox rendered in the background as in the previous examples. And we have this 3D texture display on the cube. Okay. One thing I didn't mention is that currently I don't have support for resizing the surface that I'm using you display on the window. So we are always using the same surface, which means that if you're stretching this, you definitely see that the resolution of the surface is not changed. I guess, yeah, you probably see that on the recording anyway. So you have those jaggy edges. We'll have to undo that at some point. After the texture 3D, what do we have? Equi-rectangular simple. This one was a bit, yeah, I was not really motivated to provide the implementation for that, because I don't really see the need of this feature, because the idea is just to be able to render a cube map using well, those equi-rectangular images. I didn't even know that was the name we would use for that. Maybe I can show you what this images is looking like, if I can remember which one it is. So now we're going to be in dist, assets, textures. It's this one. So this is one of those equi-rectangular textures, and you can use that actually to render a skybox. And this is what we did in this example, except that the implementation is not really correct, because I had to adapt a bit, and I'm not fully understanding what I'm doing, I believe. Equi-rectangular. So you see in the background we have this texture, the skybox. The skybox itself is looking fine. And the cube itself is kind of looking fine too, but you will notice that when I start moving too much, I get the cube out of synchronization with the background. So it means that, yeah, I'm not controlling properly the field of view for the skybox image, in the position of the camera relative to the cube. Everything doesn't really match. So we will need to go into investigation for that. But as I said, if it's just to draw a skybox, I think I could just as well use those cube maps. So yeah, not really a priority for me for now. Maybe just mentioning the shader itself, because it's worth seeing the kind of complexity that we have here. So we have this dedicated subfunction main image, which is going to do the sampling on the texture. And I think, do we have already there? Yeah, base util. This is something I have introduced afterwards, but yeah, I will come back to this. Where was I? Here, okay. Anyway, after this one, yes, we have introduced also support for basis universal texture format. These are the basis texture that we have here. And yeah, again, a relatively simple extension to the texture loader system. I'm just curious if this example is still working, so let's try it maybe. As I don't really remember the name of the example, I think I should check. Okay, just WGPU basis U. Okay. Okay, so yeah, the texture loading is working. This texture here is from the basis file. One problem I have here is, as you can see, if I try to move this way, I'm not seeing the rendering of the left side of the cube. Same thing if I move up, I'm hiding some of the rendering behind here because yeah, something to do with how I deal with the blending setup for the rendering here. I'm probably not really blending anything correctly. Or I have disabled the rendering of the back face maybe also. I'm not quite sure. It's not a big deal here. I don't really need to fix it. But yeah, it's understandable issue. Anyway, yeah. Next one. Reverse Z. This one again was a bit tricky, I would say, to implement. On the long run, maybe that's going to be something useful. The idea is basically to reverse the order of the Z buffer, so you can get more precision, in fact, for when you're close to the near plane. But nah, I could not really say that. It's tricky to set up now because the way I've implemented that, it's not really a big deal. Let's just have a look. So you're going to create your camera, and in fact this camera now is actually handling two projection matrix. So you have one for normal Z ordering and another one for the reverse Z order. And so when you're uploading the buffer to the GPU, you're providing in fact those two matrices, and then it's at runtime when you do the compilation of your shaders that you're going to decide if you're in a reverse Z configuration or not. And is this maybe where I started to introduce maybe not directly, maybe yeah, because this is coming later, because at some point I decided, okay, I need to really work on my shader pre-processing engine to add support to include different shader file in a given file, to add support for those if, def, and if, or else, or whatever. And yes, I have refactored the reverse example accordingly after that. But let's just have a look at the refactored version. So as I said, the camera will contain two projection matrices. And also next, when you do the setup here, we have a first render pass, and this one is actually using only half of the viewport, I mean off the screen, with a viewport which is half the size of the target texture. And then you have another render pass which is using the second half of the screen, but on this one you add a definition which is in the reverse Z, and those definition in fact is a mechanism that I have introduced that is allowing me to define elements in the shaders directly. So when you have those two render passes defined, you just build a render node with a skybox. In this case, you're going to add the skybox to both of those render passes. Then you're going to render the planes. So that's you actually only have one shader file here, but it's going to be compiled differently depending on the definition that I provided. So when you first add that to the first render pass, you have the first compilation stage, and that's producing one version of this file. And then in fact we go into the reverse Z mode, but in to support that properly, we also need to change the def state compare function in this case. So that's why we do it after we have added the first version to the first render pass. But you just change the def state in this case. You keep everything else unchanged. And you finally add that to the second render pass. So let's just have a look at this shader file. So we now, as I said, start to have also include. So base utils is going to include this file, the complete file here. And in there, you actually I have quite a lot of additional defines. So for instance, we find this one. This is where you define what is the far and near Z plane differently depending on whether you're in reverse Z or not. We have another location where we use this. Yes. Yeah, that's it. When you are to get your projection matrix from the camera uniform buffer, depending on whether you are in reverse Z or not, you're going to use this reverse projection matrix that I mentioned was provided by the WGPU camera, or you're going to use a regular projection matrix, which is here. And same thing when you get view projection, you do this path or the other one, depending on your the state for this flag. So, and yeah, that's how it's working. Let's get back to the CPP file and let's try to run that. GPU. So on the left side, we have the version with the regular Z buffer, and on the right side we have the same rendering, but this time using the reversed Z buffer. So indeed it's helping to reduce the flickering and the artifacts that you can see here, because two surfaces, to the red and the green surfaces, are very close one to another in this case. And yeah, we can still move around. And that's it. Okay, what else? The next one was about wireframe and thick line rendering. Creating storage buffer. This was another interesting thing, I believe. Is this where we introduce vertex pooling? Could be. Yes, I mean, that's the idea, because when you do the rendering of the thick wireframe, for instance, each line that we see here is actually a quad, a rectangular quad. So you need to draw 6 vertices per edge of your cube model, and this is where you use vertex pooling. The vertex pooling idea is basically, well, you put the vertex data not in a vertex buffer that is attached to your pipeline anymore, but in a storage buffer, and then you use the vertex indices in your draw call to decide what vertex you're going to pull from this storage buffer, which means that, for instance, if you're rendering your index number 3, normally you would have access to your vertex data number 3 from the vertex buffer, but with this technique you can decide, okay, for vertex number 3 I would in fact prefer to still use the data from the vertex number 0, and then I would use the data from whatever. So you can build much more complex logic, and this is how we have done this implementation here. I didn't know about vertex pooling yet, because actually there was no real storage buffer in the old version of OpenGL or DirectX, so makes sense. But it's a very cool thing, I believe, and I'm probably going to reuse that. What should I do? Should I do a demonstration of that? Oh man, we already have 40 minutes, so no, let's just look at the picture. They are very nice. Basically, that's the rendering that we get. This is a normal wireframe rendering. We're just going to render lines. I don't think we can control the width of the line in this case with WebGPU yet. And that's why if you want to control this, you have to resort to thick wireframe rendering here. Okay, next we're working on this off-screen rendering example, and that's where we have introduced, in fact, a bit of a more complex GLTF model, the dragon in this case. So let's just try to run this one, which is going to be off screen. So we have a nice dragon, and you have this surface which was supposed to be a mirror, but it's not really a mirror because yeah, you see that the skybox is not really behaving as we would like it to behave, and even the reflection of the dragon is not correct. But yeah, that's at least a demonstration of render to texture, because you do the rendering of the quad surface here first, and you apply that as a texture. Then when you when you render the full scene. What could we do about the code itself? Not so much. Create a render to texture pass. Okay, we're going to render the stuff in there. Then you create a normal render pass, and you're going to draw the skybox, draw the dragon, and also draw a quad, which is a simple plane here. And then yeah, when you are at render time, you will execute the first render pass, which is going to be this one. So that's going to update your render to texture. And the render to texture, I guess we're using it somewhere. We have to, right? Yes, render to texture pass, get attachment texture, and this is used as an input to the texture here to be applied on the plane. And yeah, this is done in the second pass, where you render the skybox, dragon, and the plane. Alright, and we're getting close to the end. Cool. So the last one we need to mention is a stencil buffer example, where we have another example here of the rendering that we got. I guess we can just run that also. I'm just wondering if it's stencil or stencil buffer. Nope. Better. And here we go. So for this one, again, the stencil buffer is something I've never really used myself before. I had kind of an idea of what this was about, and with this example, this helped me to clarify a bit how it's working. So basically what we're doing here, we're rendering the model that you see here in red with a kind of cartoon shader actually. So it's not, well, you have only 1, 2, 3, 4 level of red. And so when you render that, you also use a stencil buffer to write a value for each pixel where you have done a rendering for this model, basically. And then you do another render pass where you take your model and you in fact scale that a little bit to make it a little bit bigger than what it was before. And you are going to do a rendering again, but this time you're going to use a stencil buffer to figure out, okay, the pixel that I'm currently considering in fact was already rendered previously with the first pass where I rendered the red model, or is it one of those pixels that are slightly outside of the initial rendering? And if it's slightly outside, then you're going to display a color and keep your output. Otherwise, you're going to discard all of the pixels that were previously rendered anyway with the model at its original size. So that's how you use the stencil buffer, to keep information from one rendering of an object to another subsequent pass or something like that, I would say. In my words, at least, and how I understand it. If we could just maybe have a quick look at the code itself, maybe it's not that tricky. So what do we do here? We have a first pass. We're going to clear the stencil value to 1, and main render pass, compare always, replace. So basically, whenever you do the rendering of your model, you replace the value by the default stencil value. Default stencil value is actually 0. This is something I didn't really understood at first, so I've been looking for it, and in WebGPU at least, probably in the other drivers, yeah, it's 0. So that's why we're clearing to 1. It means that the full screen is initially set to 1, but then when you do the rendering of your model in the first phase, you're going to do the comparison of your stencil value with the currently stored stencil value, and your stencil value, reference value, is 0. And whenever, no, that's not how it's working. Comparison here is, I don't remember. You need to check that. But anyway, if whether it's failing or passing, you're going to replace your stencil value with the reference value, so 0. Then in the second pass, what you're going to do is, yeah, that's a stencil value that you're comparing. You're always comparing the stencil values here. So if it's not equal, it's going to pass. So you're going to replace. What do you replace here? The pixel value, the color itself, not only the stencil, right? Okay, I'm still learning. Something like that anyway. If it's passing, you do a replacement. If it's failing, you keep what was previously rendered. So you discard your fixed color, which is outline color, right? And yeah, roughly speaking, that's the idea. And I thought I was really understanding that, but now, I don't know, maybe I'm a bit tired. I'm not sure about anything anymore, but we don't really need to clarify just every single point. So let's say that's good enough. It's looking nice. So you see that, yeah, the outline itself is getting bigger because it's actually depending on the size, the scaling that you apply on your model, which is a fixed scaling. I don't remember what was the value of that. it's definitely not this 1/3, it's something else. Come on, where do you have the scaling offset? Oh, that's it, right? No? Matrix, a new path vector here, make QBO. I guess it's in the outline itself, so I would use the scaling, then it's not something that I'm fixing on the mobile. Outline, which, yes, you start with your current position, you have a normal for your point, and you move slightly in the direction of normal, so moving the pixel, the vertex outwards. Which is not really a scaling effect if you think about it. Or is it? No, not quite, depending on the normals, I guess. Okay, so this was it for the stencil buffer example. And after that, yeah, I have been working lately on the text overlay rendering. But this one, yes, I'm going to keep that for another recording, where we will probably start with a quick overview of what was done already, and then we'll try to jump directly into additional coding because it's still in progress. For this one, I'm not really following the implementation that I could find in the C version of the examples, because this is drifting a bit too much away from what I want to achieve at the end. And yeah, I thought that I was maybe ready to try to build something on my own. We'll see if this was a good idea pretty soon. Anyway, thank you for watching so far. If you managed to hold until the end of this recording, you're really motivated. And so see you another time, and meanwhile, happy coding, and bye bye.